Greetings everyone. Welcome to the third part of the lecture 3 of your Tripoli 23. This lecture 3 is about electric flux, Gauss law, and the divergence theorem. And from part 2, from the second part, I discussed the divergence of your electric flux density, which actually results into your volume charge density. And this is Maxwell's first equation in electrostatics. So this is the point form of Gauss law, or we can say that the Gauss law is the integral form of Maxwell's first equation. We went through some examples proving the use of the divergence. In the case of a point charge, well, if we take the divergence of the electric flux density of a point charge like this, we know that it's this expression. If we take the divergence, we get 0 everywhere, which means that there are no charges in space if we draw that. So this is your point charge. There is no flux anywhere else except for, sorry, there's no charge anywhere else except for the origin, where you have an infinite charge density. Since it's a point, it has no volume, then but it has a charge q. Divide that by 0, it's equal to infinity. Okay. Next example, I shown you how to use the divergence for a given electric flux density. You can solve for the volume charge density just by your divergence, okay? And it looks something like this. Now let's define the vector operator, okay, del. We call this inverted triangle del. So that is called uh, the del operator. So take note, it's an operator, okay? Kind of like your addition operator, plus. By itself, it doesn't mean anything. What you're gonna do with plus. But if we add operands, in this case, let's use 2 and 3. Now it makes sense because it's an operator. If we add operands, it makes sense. But by itself, your vector operator del doesn't mean anything. But its equivalent notation, at least for your Cartesian coordinates, looks like this. It characterizes the change, okay, the change of your quantity in the x direction, the change of your quantity in the y direction, and the change of your quantity in the z direction or the z direction. So it's a vector operator since it has an x, y, and z component. Right? So if you have a certain, it uh, kind of unifies or makes sense of the change in the vector from a point P and a point Q. Right? How does your vector change over the next point? Okay? So in what direction, in the x direction, in the x direction, how much did it change? In the y direction, how much did it change? And in the z direction, how much did it change? You can think of it that way. So it's the change over the length of a very small length of x in the x direction, in the change in a very small length of y in the y direction, and the change in a very small length z in the z direction. So with this defined, we can actually express the divergence of an electric flux by using the dot product. Okay? So if we let D be expressed in Cartesian coordinates, it has an x component and a y component and a z component. Right? Something like that. And if this D is expressed in your Cartesian coordinates, okay, then if you get the dot product between your del operator and your vector field D, we get this expression right here. So the x component will interact with each other. There should be no direction here. No direction here. Y components will interact with each other, and the Z components will interact with each other. So it's a partial derivative of your X component with respect to X plus the partial derivative of your Y component with respect to Y plus the partial derivative with your Z component with respect to Z. Okay? This is the divergence. It's what we got. That's what I showed you in the previous lecture. For the Cartesian coordinate, this is the divergence. Alright. So, with this, for more information, this del operator can actually be used in scalar fields too. Okay? If we multiply del with respect to u, a scalar field u, it's just the same as distributing that u to each component. Okay? So kind of like just a scalar multiplication, and we get a vector result right here. This characterizes the change in your scalar field in the x direction, this change in the y direction, and this the change in the z direction. We call this the gradient of u. Okay? So it characterizes the change along different directions of your scalar field. Okay? So um, for different coordinate systems, according to the book, your del does not have any specific form for cylindrical and spherical. But we can still indicate del dot d as the divergence in other coordinate systems. Okay. Now, this is the statement in the book. We will follow that, right? But I beg to differ, actually. We can actually express del in your cylindrical coordinate system and spherical coordinate system. But just note from this on this derivation, I I am not basically I'm not using the textbook as a reference. Okay, so just a disclaimer, right? This is just what I found in by reading different parts in the internet, and basically, and actually some part of it is just me thinking. All right, so I'll show you. Okay, so the definition of del or nabla in the Cartesian coordinate system is basically the change in different components of your vector. Okay? The change in different components of the vector with respect to the quantity or the unit length in that direction. Okay? So, right. So, for a Cartesian coordinates, basically, if you want to look at the change along the x direction, you get the partial derivative with respect to x. Same is true with ay and az. Now, if we try to translate that in your cylindrical coordinate system, okay, so your nabla becomes a sum of components in the a rho, a phi, and az directions. Z component, still the same. If you want to get the change in the unit length along the Z axis or the Z component, then you just get the derivative with respect to Z. For your rho component, you're just basically changing the radius of your cylinder. Therefore, you're getting the change of your vector with respect to the rho component. Excuse me. So the change with respect to the rho component. Okay, so you're moving along the length of rho. And this is the differential length of your rho axis. For the phi, it's a little trickier Because if you're changing your phi component, you're actually looking or moving along the circular path on a cylinder. So if you're gonna look at the change of your vector along the length of that circle, you're actually differentiating that vector or that quantity with respect to the arc length. Let's call it S. And this arc length is, since it's a circle, it has a constant rho, which is the radius, and you have a differential angle, which is d phi. So this is the expression of your del in cylindrical coordinates. Similarly, we can actually get the uh, the del expression in um, spherical coordinates. Okay, so we're looking at AR hat, A theta hat, and A phi hat. A phi hat still the same, but instead of using rho, we're looking at the radius r sine theta. Okay, since this will be the radius of the circle along that sphere. Okay, now for theta, again we're moving along the length of the uh, circle that is defined by theta. So that's movement along the arc length. Let's call it partial s again. In this case, it's just partial theta multiplied to the constant radius of your sphere. And finally, for AR hat, you're just changing the length of, you're just moving along the radius of the sphere. You're increasing it or decreasing it. And it's just the movement along that axis. So it's simply partial of AR hat with respect to R. Okay? So how does this work for us? We can actually use these values to, or these definitions to derive the divergence with respect to your cylindrical coordinate and spherical coordinate. So let's consider the cylindrical coordinate. Right? We get the divergence of a vector field with that is expressed in cylindrical coordinates. There you go. Okay. So if we get this expression, well, we can substitute your rho, your nabla, or your del with this expression in cylindrical coordinates. Right? So something like this. Okay. So let's consider the first term. Okay. Oh no. Just a minute. There you go. So the first term is equal to this expression right here. Okay. So we distribute this expression into the each component. So just distribute that to this, to this, to this. Okay. So it will look like something like this. Okay. So we just repeat that. Okay. And change the terms something like this. Okay. So we get the dot product of each, and by the property of your dot product, we can let this scalar quantity interact with this, or basically we factor this scalar quantity out and change it and let it go here. Okay, so we do that to each uh, component, something like this. There you go. And same here. Why? So this is a property of the uh, dot product where your scalar quantities can be transferred into the next term. So now we have something like this. Your arrow hat dotted to this expression, which is getting the partial derivative of this whole expression. Take note, this whole expression right here with respect to rho. Same is true with this. Same is true with this. Okay? So what does that information give us? Well, basically, this component here, the whole component, should be uh, evaluated with the derivative. Okay? Since arrow hat, recall that arrow hat, or the raw direction, changes with respect to phi, then this whole expression here is we cannot factor out arrow hat from this derivative right here, like so. Okay, since arrow hat changes with respect to your phi component, right? In this case here, arrow hat here can be factored out like so. Arrow hat here can be factored out like so. Why? Because the direction does not change with rho. So if you move along rho, the direction of arrow hat does not change. If you move along z, sorry, not z. This should be, yeah, sorry, correct. If you move along z, arrow hat also does not change. So we can factor that out. But in this case here, you can't factor this out here. That's a no-no because arrow hat changes with phi. Okay? So this dotted to this dotted to this will be 0. Okay? We're left with these terms. So let's write that down. Something like this. Okay? So arrow hat dotted to arrow hat. You'll just be left with this. Something like this. Okay? Now, in this expression right here, we're gonna use the uh, multiplication property of derivatives, where this expression becomes derivative with respect to rho, okay, something like this, plus, okay, oops, sorry, the partial derivative of your arrow hat times 0. So this is the multiplication property of your derivative. Now, since if we distribute this a phi hat dotted to this and dotted to this, okay, so a phi hat dotted to arrow hat is not possible. So this will be 0. So not really not possible, sorry, not thinking straight. Arrow dotted to a phi is 0 because they are orthogonal. Okay. Now for this expression right here, we're getting the derivative of arrow hat with respect to phi. So basically, what is the movement of arrow hat when we move along phi? Recall that arrow hat is actually equal to, in terms of your Cartesian coordinates, since your Cartesian coordinates does not change with respect to phi, we can use that to our advantage. So arrow hat is equal to this There you go. So if you take the derivative of both terms, the derivative of this is negative sine ax hat, and the derivative of this is positive cosine phi ay hat. So this derivative term will disappear. Okay, something like this. And this term inside is actually the definition of a phi hat. Sorry, a rho. Sorry, yeah, correct. A phi hat, or the phi direction. Therefore, this dot product here will now be equal to 1. Okay, and you're left with these expressions right here. The partial derivative of rho with respect to rho, the rho component with respect to rho, times this expression right here. Okay, d rho over rho. Something like this. And this can actually be expressed as oops. Oops, sorry. There you go. And this is the rho component of your cylindrical divergence. Right? The rho component of your cylindrical divergence. Okay. So if we're gonna do that with all terms, we're gonna get the divergence in cylindrical coordinates. Okay. So that is how we express this del in terms of cylindrical coordinates. If you're gonna do the same, you can do the same in the spherical coordinates. Okay. So I'll leave it at that. So going back. Okay. Now recall Gauss law. Let's go back on track. Recall Gauss law, where you have the enclosed charge equal to the closed surface integral. Okay? Since the total charge is equal to the volumetric integral of your charge density times the volume, and we have the del, the divergence of d equal to the charge density, then we can express this in terms of this. And this is called the divergence theorem. So the divergence theorem is the integral of the normal component of any vector field over a closed surface is equal to the integral of the divergence of this vector field throughout the volume enclosed by the closed surface. That's what's said here. Okay, so I just read that out. That's a lot of effort, you know. Kidding. All right, so we have something like this. This is the divergence theorem. What it says is that if you have a volume, let's say a cube, okay, there's a flow of vector field going out of that cube or going into the cube, whatever. Okay, if we're gonna get the divergence of the field in this region, you're gonna get a density inside the region, and this uh, the total volume of that density is basically equal to the total flux of the uh, field lines going through the surfaces of that volume right there. Okay? So let's just have some examples. The divergence theorem. So given an electric flux density, what is the total charge enclosed by the surface R is equal to 1? So we have two methods here. We can get the total charge enclosed by doing a surface integral. Okay, so let's do that first. The differential surface is this, since it's a sphere, and that is bounded by these values. Okay, we integrate that. So we let r equal to 1. your theta is from 0 to pi, your phi is from 0 to 2 pi, integrate that, you get 3 pi squared coulombs. To confirm this value, we get the divergence of the field. Okay, so we get the divergence, the del dot D, you get this expression. Solve for the divergence, you get the volumetric charge density is this. Integrate that with the expression of the sphere r is equal to 1. Sorry, this should be 1. Okay, and the bounds of the integral becomes 0 to 1 of r. Your theta is 0 to pi, and your phi is from 0 to 2 pi. Okay, so you integrate that expression with the volume. Okay, and then separate the variables since it's just a sphere. With that symmetry, you can separate the variables easily. And compute, you'll get this. So that means if you can use this actually to verify your answer. If you get the same answer for both cases, the right hand side, this side, and this side, that means your answer is correct. So another example. In the region of free space, we have this flux density. Evaluate both sides of the integral of the divergence theorem. First, solve for the divergence. We get this expression right here. So get the volume integral. Since it's just a cube, you can easily set up the integral. So it's just a cube. So from 2 to 3, the x, y, 2 to 3, z, 2 to 3. You can separate the integral easily. The x variables will just remain with the x, y variables will remain with the y, and z variables will remain with the z. And you'll get this expression. You can solve for the total charge of that volume. You get 125 over 36. Now, we're looking at the cube, something like this. We're gonna calculate the surface integral of that cube. Therefore, it's easier to divide that task by looking at the faces of the cube. Left and right, front and back, top and bottom. If you look at the left and right integrals, um, that is on the direction of ay and negative ay and positive ay. It should be ay. Okay. So if we evaluate that integral with each other, we can show that these two are of equal in magnitude but opposite in sign. Okay. So that means they cancel each other out and become 0. Same is true with the front and back, which is along ax hat and negative ax hat. So something like that, also 0. For the top and bottom, it's different. Okay? For the top and bottom, it's along az hat and along negative az hat. So if we evaluate the integral with the bounds of your x and y, so x is from 2 to 3, y is from 2 to 3. Same here. So evaluate that, you'll get this expression right, not expression, this result right here. And the total flux is to just add all the flux of each face of the cube. The total flux is 125 over 36 coulombs, equal to the total charge, and proving that, not really proving, and showing that these are equal, then probably you have the right answer. Right, so that you can use this theorem to verify your answer. Right. So if you have any questions, leave some comments in the comment section below or this video. Okay, so the next this will be the last topic to be covered for the first long exam. All right, and then if you have any questions, if you want to discuss anything's not clear, please comment. Don't hesitate to comment. I'll try to accommodate your questions and answer them as soon as possible, as soon as you comment on them. Right? So I'll see you in the next meeting.